Look up at the night sky, and the stars seem entirely permanent. But a star only survives through a violent, continuous physical stalemate. Inside that massive core, millions of tons of matter are crushed inward by gravity every second. The only thing keeping the star from collapsing is the intense heat and outward radiation of its own nuclear fusion. As long as those two forces balance out, the star holds its shape. In 1930, a 19-year-old Indian physicist named Subrahmanyan Chandrasekhar boarded a ship bound for England. He was carrying little more than notebooks and equations. But during that voyage across the Arabian Sea, he began calculating the exact mechanism of how a star actually dies. At the time, astronomers thought they had stellar death completely figured out. When a star finally exhausts its nuclear fuel, the outward push of radiation stops and gravity takes over. The star compresses down into a dense, Earth-sized remnant known as a white dwarf, where it simply sits and cools off indefinitely. It was a neat, comforting conclusion to the life cycle of a star. But Chandrasekhar's math showed that the scientific establishment had missed a massive variable in their equations. The assumption that a dead star would just safely stabilize forever was mathematically flawed. To understand the flaw, we have to look inside a white dwarf. Imagine compressing a star roughly the mass of our Sun into a sphere the size of Earth. The matter inside becomes so incredibly dense that atoms are crushed together. Ordinary gas pressure completely breaks down. Instead, physics shifts to the quantum realm. Specifically, a bizarre effect called electron degeneracy pressure takes over. According to the Pauli exclusion principle, two electrons cannot occupy the exact same quantum state at the same time. As gravity crushes the matter tighter and tighter, these electrons fiercely resist being forced into identical states. That quantum resistance creates a physical force. It generates an immense outward pushing pressure that fights back against gravity. And because this is a mechanical quantum effect, it operates entirely independent of the star's heat. Even a freezing cold white dwarf can hold its shape. But quantum mechanics only provides a temporary defense against gravity. Chandrasekhar realized that if you keep adding mass to the star, this physical stalemate must eventually reach a breaking point. The breaking point comes down to velocity. As a white dwarf gets heavier, gravity pushes down with even greater force. To maintain that quantum resistance and avoid occupying the same state, the densely packed electrons are forced to move faster and faster. This chart plots outward pressure against electron speed. As velocities approach the speed of light, line C, special relativity kicks in, and the curve flattens. The math breaks down. Quantum pressure cannot match the compounding force of gravity, and the balance completely fails. Using stellar structure equations, Chandrasekhar calculated the exact threshold where this failure occurs. Today, it is known as the Chandrasekhar limit. Any dead star heavier than roughly 1.4 times the mass of our Sun cannot physically support its own weight. The implication of this number was highly disturbing. It meant nature permits the existence of massive objects, where gravitational collapse never truly stops. Something far darker than a white dwarf had to exist. The mathematics were rigorous, but the accepted physics community completely rejected the idea. They found absolute collapse too absurd for nature to allow. The pushback was led by Arthur Eddington, one of the most authoritative astrophysicists on Earth. During a major Royal Astronomical Society meeting in 1935, Eddington publicly attacked Chandrasekhar's conclusions, arguing that some unknown law of nature must step in to prevent this behavior. It was a devastating humiliation for the 19-year-old Indian scientist. He was already navigating the severe barriers of the colonial era. He sat watching one of the world's most powerful physicists effectively declare his life's work physically impossible in front of his peers. But the equations did not care about Eddington's reputation. They did not care about human authority, or how uncomfortable the physics community felt about the extremes of the universe. It would take decades, but astronomical observations slowly cornered the scientific establishment. The data relentlessly pointed to the precise realities that Chandrasekhar had calculated. First came the discovery of neutron stars. If collapsing matter becomes dense enough to break past electron degeneracy pressure, the extreme gravity literally forces protons and electrons to combine. They fuse into neutrons, packing a star's mass into a sphere just 20 kilometers wide. But even neutron stars have their limits. If the collapsing core is massive enough, not even neutrons can resist the crush. The star collapses further. Escape velocity exceeds light speed, and space-time curves inward. A black hole forms. Chandrasekhar's 1.4 solar mass threshold became the critical mathematical gateway. It provided the strict physical boundaries that allowed modern black hole astrophysics to formally emerge. Eddington's intuition was simply wrong. Nature does not protect us from extreme physics. The universe actively creates the precise cosmic monsters he was so desperate to ignore. And sometimes, crossing the limit results in a different kind of extreme. If a white dwarf approaches the Chandrasekhar mass by actively stealing gas from a companion star, it triggers a runaway thermonuclear explosion. Entire stars detonate. Because these specific explosions, known as Type 1a supernovae, always trigger exactly at that 1.4 mass threshold, they erupt with a remarkably consistent brightness. Astronomers use them as standard candles to measure vast distances across space. By tracking those predictable bright explosions, researchers were eventually able to map the cosmos. Those measurements led directly to the discovery of dark energy and the accelerating expansion of the entire universe. 53 years after his solitary boat trip across the Arabian Sea, Subrahmanyan Chandrasekhar was awarded the Nobel Prize in Physics. The calculations he defended against the entire scientific establishment are now foundational physics. Hidden inside every seemingly permanent star is a mathematical tripwire. Below the limit, matter survives. Cross it, and familiar reality gives way to the abyss.